So dear students, today I am going to speak on a very important and very interesting topic, crystal field theory or CFT. So before going to this theory in detail, I just want to highlight on certain points that will help you in understanding the subject better. So crystal field theory is basically due to the electrostatic force that is operative in between the metal ion and the donor atoms of the ligands. As we know that when the metal ions and the ligands are free from each other, means when they are isolated, then the energy associated with those species are very high, means they are very much unstable. So obviously there will be a tendency for both the species to get attracted by each other in order to form coordination complex. And by doing that, it will minimize the energy of the system. So here is a energy diagram for this system. So it is seen that when the metal and the ligand are separated from each other, in that case, the energy of the systems were very high. But as soon as they form a metal complex by uh, by forming coordinate covalent bond between the metal and the ligands, the energy of the system reaches the minimum. But at the same time, there occurs a repulsion between the ligand and the d electrons present in the metal, uh, which will result in a sudden increase in the system, and that is indicated by this line. Afterwards, there is a further splitting of the 5d orbitals, which were initially degenerate due to the presence of ligands. Particularly in an octahedral geometry, these 5d orbitals will split it up into two sets of orbitals. One set will contain two orbitals and the other set will contain three orbitals. And this separation between these two sets of orbitals is the basis of crystal field splitting. So crystal field theory describes the bonding in metal complexes. There are certain assumptions for this theory. So electrostatic, it is basically, as I have already mentioned, that the electrostatic interaction between the ligand and the metal d orbitals. And the most important thing is that the ligands involved in these coordination complexes are treated as negative point charges. Further, it should be noted that when the ligands are at infinite distance from the metal center, there will be no effect of ligands on the d orbitals. Means these are the directions. These are the directions from which the ligands will approach the metal center. This is the metal center, and these are the directions from where the ligands can approach the metal center in an octahedral complex. So, these ligands, when they are far away from the metal center, then these ligands will have hardly any effect on the d orbitals. And at that point of time, all the 5d orbitals will be degenerate. And it has been observed that the d orbitals aligned along the octahedral axis will be affected the most. So when the ligands are coming closer to the metal center, then the d orbitals which are in the direction of the ligand, which are present in the direction of the ligand, will be affected the most, and as a result, those orbitals will be raised in energy. Their energy will be enhanced. The metal d orbital which is attacked by the ligand will be raised in energy. But the ligands, orbitals which are the d orbitals which are lying in between the axes, means which are not directly in the direction of the uh, ligand approaching direction, they will not be affected that much, and hence their energy will be little bit lower as compared to those orbitals which are present directly in the direction of the ligand. So, uh, so, uh, so these are the 5d orbitals. Out of these 5d orbitals, here we can see that these orbitals, particularly dz square and dx square minus y square, these two orbitals have lobes pointing directly towards the axis. Say this is the dz square orbital, and its lobes are pointing directly towards the z-axis. On the other hand, the dx square minus y square, this orbital, it has also lobes which are pointing directly in the direction of the axis. So, when the ligands approaches the metal center, these two orbitals will be affected the most, and hence their energy will be raised. On the other hand, the other three orbitals, namely dxy, dyz, and dzx, these orbitals have lobes pointing in between the axes. Since the ligands are not approaching the metal center in this direction, where these ligands are present, they will not be affected much, and hence their energy will be less as compared to that of these two orbitals. So this is a clear picture to understand the effect. So this is how the ligands are approaching the metal center. Here you can see that this is the dz square orbital, and this is the dx square minus y square orbital. These two orbitals will be raised in energy because their lobes are pointing directly in the direction of the ligand. But these are the other three orbitals, other three d orbitals, whose lobes are not pointing directly in the direction of the ligand. They are in between the axes. So they will feel lesser repulsion when the ligands approaches the metal center. And as a result, their energy will be lowered as compared to these two orbitals. So hence, a separation between uh, the 5d orbitals take place. It forms two sets, as can be seen from this figure. One set contains 3 orbitals, and the other energy state, other state, other set contains 2 orbitals with high energy. Now, so this is how the splitting takes place. This is a set of orbital containing dxy, dyz, and dzx, and this is a set of orbital containing dx square minus y square and dz square. And the energy gap in between these two sets of orbitals is known as delta, or 10 dq, or it may be called as the crystal field splitting energy. So that dz square and dx square minus y square orbitals lie on the same axis as negative charges. Since these orbitals are nothing but these are the shelters of electrons. And as we know that the electrons are negatively charged, so these orbitals can be treated as a negative charges. All these orbitals can be treated as negative charges. Therefore, there is a large unfavorable interaction between the between ligand orbitals. So already I have told you that CFT assumes all the ligands as a negative point charges. So the ligands are negative and the d orbitals are also negative. So there will be obviously there will be a repulsion, electrostatic repulsion in between these two species. These orbitals form the degenerate high energy pair of energy levels. Means since as I have already discussed that these two d orbitals will experience more repulsion, so their energy will be raised as compared to these three orbitals. The dxy, dyz, and dzx orbital bisect the negative charges because they are not directly in the direction through which the ligands are approaching the metal center. Therefore, there is a smaller repulsion between the ligand and the metal, what is orbitals. So these orbitals generate low energy set of energy levels. The energy will be comparatively lower than these orbitals. Now, there are certain factors on which this crystal field splitting means crystal field splitting energy depends. Means the gap in between these two sets of orbitals may be varied depending upon certain factors. So mainly, firstly, it depends upon the metal. It depends upon the nature of the metal. What is the metal? The metal involved in the coordination complex will tell you whether it is going to split more or less. So larger metal ion gives you larger delta value, means it causes larger crystal field splitting. Means the gap in between the two states of energy, two sets of orbital will be more than higher oxidation state of the metal. Suppose we have two oxidation states, say Fe2 plus and Fe3 plus. Same metal, but oxidation state is different. So according to this, if the metal atom is in higher oxidation state, then it will cause larger splitting as compared to the splitting caused by the lower oxidation state. Means Fe2, if you compare the splitting pattern of Fe2 plus and Fe3 plus, then we can see that Fe3 plus will cause more splitting as compared to Fe2 plus. Then ligands, it also depends upon the nature of the ligand, what type of ligand is present in your compound, that also affects, and that is what is known as the spectrochemical series. In my earlier video, I have discussed about that, what is spectrochemical series. So basically this is the series. I have not given all the, I have not mentioned here all the ligands. A few important ligands have been included here. So you can see that these red, the ligands which are marked red are relatively weak field ligands, and the one which are marked green are of middle strength, and the ligands which are present in the extreme right and also marked in blue are strong field ligand. So weak field ligand, they causes small crystal field splitting because they have low electrostatic interaction. They causes low electrostatic interaction. On the other hand, high field ligand, or strong field ligand, they causes large crystal field splitting because of the strong electrostatic interaction. So here is an example. You can see that chromium F6 3 minus. So this complex is having 3 electrons in its outermost shell, outermost d cell actually, d orbital, outermost d orbital. So these 3 electrons will be occupying the lower lying orbitals. All are singly filled. The same is the situation in CrH2O6 3 plus. See, all these examples uh, carries the same metal ion. All these complexes carries the same metal ions, but the ligands associated with the metal ion is different. Here it is F6, 6 fluoride ligands are there. Here 6 water ligands are there. Here 6 ammonia ligands are there. Here 6 cyanides are there. So that is the difference. Rest of the thing is same. Oxidation state in this chromium is +3. Here also it is +3. Here also it is +3. Here also it is +3. But here you can see that the gap between these two sets of orbital is different. Here we can see the least crystal field splitting. That means the delta value is minimum here. But if you move to this compound, the crystal field splitting is little higher, little bigger, little more, which is even more in this particular compound, CrNH36. And this is maximum in CN6. So this is because in this complex, chromium is associated with 6 cyanide ions. Cyanide is, as we know, that it is a strong field ligand. It is at the extreme right of the spectrochemical series. So it causes maximum splitting. The energy gap in between these two sets is very high. On the other hand, fluoride, chloride, these are weak field ligands, as we know. And so they causes less splitting, and hence the energy gap between these two sets are very less or very low. Now, how to fill the electrons in the d orbitals? As we know that transition metals have its outermost cell electronic configuration, this n-1 d1 to 9 ns1 minus 2, as we all know it. So when it get oxidized, the metal get oxidized, it gives up electron from the ns orbital first. So titanium, for example, titanium, in case of titanium is a D2 system actually, ns2 n-1 D2. So +3 state of +3 oxidation state of titanium carries only 1 electron in the D1 system, D1, d orbital, because 2 electrons from this ns orbital will go out along with an electron from the d orbital, leaving a D1 configuration. Similarly, vanadium in +3 oxidation state, it will have only 2 electrons in the d orbital. Chromium 3 will have 3 electrons in the valence d orbital. So, like the s and p block elements, as we know that in Hund's rule is applicable here also. As in the case of S and P block elements, we use the Hund's rule. Here also, we can use the Hund's rule. So, if you follow the Hund's rule, then you can see that the lower lying orbitals will be filled up first. First of all these 3 orbitals will be filled singly filled one by one. So if you have 3 electrons in the d orbital, then the 3 orbital will occupy this 3. If you have 3 electrons in the outermost shell, in the d orbital, outermost shell d orbital, then the electrons will occupy these 3 orbitals only. That means dxy1, dy11, dxy1, dyz1, and dzx1. But when we have 4 electrons in the outermost shell d orbital, then we, while filling up the orbitals, we'll have two choices. First one is, if the energy gap between these two sets of orbital is very high, means if the crystal field splitting is very high, then the fourth electron will occupy the lower lying d orbital rather than going to the higher lying d orbital. It will get paired up. On the other hand, if the crystal field splitting, that means the delta value is very small, means the energy gap in between these two sets of orbital is very less, then the fourth electron will occupy a higher lying d orbital rather than pairing with a lower lying d orbital. So here we can see that in this situation, when the delta value is very less, so in that case, we will get large number of unpaired electrons. Means its paramagnetic nature will be more. But on the other hand, when delta value is very high, means when the energy gap between these two sets of orbital is very high, then the number of unpaired electron will be less. Here we can see there are 4 unpaired electrons, but here we can see only 2 unpaired electrons. So in the previous case, in the first case, the complex will be more paramagnetic as compared to the second complex. So this will be 4 electron paramagnetic, and this will be 2 electron paramagnetic. So if we generalize it, then we can say that with small delta value, high spin complexes will be obtained. Small delta value means high spin, more number of unpaired electrons. On the other hand, in case of strong field ligands with large delta value, low spin complexes will be obtained. So this is how crystal field theory explains the magnetic behavior of certain coordination complexes. Now, whatever we have discussed here is about an octahedral geometry in which we can see that the 5 degenerate orbitals split up into 2 sets of orbitals, one containing 3 orbitals and the other containing 2 orbitals. But if we have some other geometries of the coordination compound, then the splitting pattern may be different. In case of octahedral, already we have discussed these 3 orbitals will have low energy and these 2 orbitals will have higher energy. Now instead of octahedral, if we have a tetrahedral structure, then the situation will be just opposite to that of octahedral one. Here you can see that dx square minus y square and z square orbital will have lower energy, but these 3 orbitals dxy, dyz and dzx orbital will have high energy. Similarly, if we have a square planar geometry, then we will have four sets of orbitals. There will be four sets of orbitals. The lowest energy set will have two orbitals only, that is dxz and dyz. Next is dz square. Next to next is dxy, and the orbital which is having the highest energy will be the dx square minus y square orbital. So this is all about crystal field splitting and crystal field theory. Uh, I will try to give more another presentation on the applications of crystal field theory, particularly how crystal field theory can be used in explaining the color of tensor metal complexes as well as the magnetic properties in detail. Thank you.